Right, in this video we're going to continue to work with limits, and this time we're going to be looking at left and right hand limits. So the main reason we're doing this video is to want to answer basically two questions. Do all limits exist? And we'll say that no, not all limits exist. At every point, no. Like on some functions there's a point where the limit doesn't exist. And from the work that we're doing today we'll be able to answer the question when the limits exist and when they do not exist. And if they do, we've learnt in the last couple of videos how we calculate the limits. So for the left hand limit here, we've got this notation here. We'll just add a little minus bit up here. That indicates that we're coming from the left. And we'll read this as the limit of f of x as x approaches a from the left is equal to L. And the same for the right, except this time it's a plus, and we're going to this number a from the right. We're approaching it from the right, and the other one we're approaching it from the left. So because we've learned about two-sided limits when we're approaching from either the left or the right, now we're talking about just the left or the right. I want to know what the relationship is between these two things. So let's have a look at that. So in notation this is basically what it means. And I'll explain this in words just in case you don't understand what this means. So we've got this limit here. This is like the general limit, and this theorem's basically saying that this exists if and only if. That's what this symbol here means. This limit from the left and this limit from the right are both equal to L. In other words, both of these limits are the same, and then this limit exists and has the same value. That's basically what this kind of theorem says. So now let's look at some examples and see if these limits exist. So here I've got the limit as x approaches 2 of 3x squared. So we know from experience the graph looks something like this. And we could have like the point 2 and be somewhere around there. And if you look from the right it's approaching 2, and from the left it's also approaching 2, because look, you can see it's coming up here to this value 2, and from the other side it's coming down here to the value 2. So from both sides it's approaching 2. So therefore the left and right hand limits are the same, and this limit at 2 exists. And we can calculate it if you like. So for some practice let's just do that. Let's just calculate this. So we can basically just plug in 2, and we know that we square this first, so we get 3 times 4. Just 12. So this limit here is 12. But don't just plug in numbers to any function and do this, because some limits don't exist. Now let's look at another example. I'm hoping that people have seen this graph before, because it's a very common graph and a basic one that you should have learned a lot about in your algebra class. it looks like this. Now, you can see that this graph looks totally different from the other one. Now, from the left, this is going up and up and up, and it's getting steeper. You can see it's getting steeper, this curve going up more and more. So this is actually approaching infinity. So this limit here from the left is approaching infinity. And then if we look at this other limit here, we're approaching from right, look, we're going down this time, so we're going down to minus infinity. So the left hand limit is infinity, and the right hand limit is minus infinity. So infinity and minus infinity are obviously not the same, so this does not exist. Okay, so that's in the class of rational functions. So we can see that from the general one, there's a problem. So when you're working with limits, be careful with rational functions. Very careful. This one here is an example of a function that's called a piecewise defined function. Now I want to show you this one because there's also a problem. So first of all, let's look at the graph and see what this looks like. So this is 1 minus x here. So that's 1 there. But then the problem is when x is greater than 1, the function totally changes, it's a squared. So it would look something like that, but not exactly, and you can see that the limit from the left here is approaching this point, and the limit from the right here is approaching this point. And if you calculate these 2 points coming approaching from each side, they wouldn't agree, because that's approaching this point, this gap here, because the limit can't jump down to here. That's just not how the limit behaves at all. So this limit also doesn't exist. I'm not going to calculate the points because we can see here that the limit doesn't exist because of the graph. I mean, look, that's not even a continuous thing. We'll see about continuous functions more general later on, but what I mean is it's in 2 parts, it's not just one curve, one function. There's a gap here, and that bit's filled in because that's the point where it's 1, not this one. But you see that one's approaching that, which is wrong. So even though it's defined at the point 1, the limit doesn't actually exist, because the left and right hand limit aren't the same. And here, that is the condition for this limit to exist at a particular point, that they must be the same, and here they're not. So that's why the limit doesn't exist. So that's all I really want to say about that. Just in general, be very careful with rational functions, piecewise defined functions, and absolute value functions. The rest of them are usually fine.